You know what they really want to do?
We're recording now? Cool. All right. So,
A Snapchat. Hard work.
it's called Open Broadcaster Software. All right, here's the review. So, these are both conducting spheres. There are a couple things that go along with that. Because they're conducting, the electric field inside of a conductor is zero. There's no electric field inside of the conductor. Part of the reason that is because all the charge is on the surface of the conductor. So if I put a charge on something, they're going to spread themselves out as far as they can possibly get. In a conductor, they can move freely around. That means as far away as they can possibly get is just to sit on the surface. And if that's the case, and I look at a point in the middle, the electric field from all sides kind of pulls and cancels each other out. There's no electric field on the inside. What do you got, Bryson?
So like if it's polarized, does that change anything?
Well, it's polarized, something's on the outside of it making stuff happen. That's not necessarily going to happen here. Okay. We're just putting a charge on it, letting it move around naturally. So all charge on the surface is on the surface of a conductor. That's why there's no electric field. We also know the potential inside of a conductor is constant. It doesn't change. First, that's what we saw in the lab, right? When we were inside that conducting shield, the potential didn't change. We got a flat spot. Also, the potential is the electric field times the distance. If there's no electric field in that area, there's no potential in that area. One of the things this means is that it takes no work to move a charge inside of a conductor. If the electric field is zero, I'm not pushing against any force to move a charge inside around here. There's no voltage. There's no change in voltage because there's no work to move that charge.
So with the equation, you said the electric field can be zero. So would that mean the voltage is zero also? Change in voltage.
Change in voltage. Thank you. Yeah, that's a good point to make. It's the change in voltage that's zero. All right. Potential electric field zero. That means the surface of a conductor is an equipotential. What does that mean? All has the same potential all the way around it. Does that make sense? That's same voltage all the way around it. Now, the other thing is that for when we're outside a spherical conductor, the charge acts like it's at the center. That's a tough one, okay. But if I'm right here and I want to know the electric field, technically there's a bit of charge all over, and all those bits of charge are contributing to the electric field. instead of having to do all that math, what we're going to do is pretend that once we get on the outside of this, all the charge acts like it's at the center. So it's like we have a 5 nanocoulomb charge located at the center of that thing once we're on the outside. It's a simplification we make so that we don't have to do all that calculus. It turns out all that calculus tells us that it acts like it is all the center.
So at that point, it'll be towards the charge, right?
Yeah. Electric field is towards the charge.
How does that?
So instead of the electric field being this way because of one piece of charge, this way because of another piece of charge, this way because of another piece of charge, it all averages out and points to the negative 5 nanocoulombs, like it's at the center. So, questions? Oh, we want to calculate the electric potential at these places. Cool. All right. So, we're calling that 0. That's 0.2. And then over here's 0.8. The 3 points that we're concerned with finding the electric field at are 0.1. Call that A. Well, we'll call that 1. 0.5, dead kind of in the middle. 2, and then at 1 meter. Is everybody okay with that? How many charges are in this region? 1. Okay, so the easiest one for us to do right now is going to be 2. The voltage is equal to KQ over R. How much charge are we talking about?
5 million.
Okay, so we have 9 times 10 to the positive 9th, that's K, times 5 times 10 to the negative 9th coulombs, divided by how far away are we from where this charge is behaving like it's at? 0.5. So that voltage comes out to be 90. Positive or negative, though? Because it's a negative charge, we're going to have negative 90 volts. Does that make sense? Yeah, you could plug in the negative 5 instead of doing that. That's fine, too. Huh?
Why is like the edge thing?
Because 1 and 3 are inside of the conductor. 2 is not inside of the conductor. So, inside of the conductor, there's no change in voltage anywhere, right? So if there's no change in voltage anywhere, the voltage at the center and the voltage at the edge are the same. Because it's an equal potential all the way through. The only place that we can calculate it is out here at the edge. Because all the charge is at the edge, and it's only until we get to the edge or on the outside that it acts like a point charge. We only know what to do with point charges. So, for all points in the sphere, points. For every single one of those points, the voltage is equal to 9 times 10 to the 9th times 5 times 10 to the negative 5 times 10 to the negative 9th divided by 0.2, because that's the voltage at the edge. So that's for all points inside of that sphere. So that voltage comes out to be 45 times 5? No. Negative 225 volts. And that's going to be for one and every point inside the sphere. But it only applies to that because that's the only thing inside of a conductor. Out here, we're floating in free space. We're not inside the conductor. Does that make sense?
So like, why does it stop at the edge also?
Oh, because there's that sphere on the edge exists in space, and so there's charge there. And when I'm out here, I still feel the effects of what that charge is doing. So it's not the voltage stops there, it's that the voltage starts to change there. Then, for part 3, same thing. We get to the sphere. the voltage is the same throughout the sphere as it is at the edge. Does that make some sense? And so here, that voltage is K, 9 times 10 to the ninth, times -5 times 10 to the -9th coulombs divided by 0.8. That voltage comes out to be negative 56.25 volts. Does that make some sense as we're going through that? I know those are numbers that you calculated before. Now, all the stuff in green was part A. Part B wants to know about the electric field.
I have a quick question.
Yes, sir.
So is this all in relation to like a circle, or like, if it's a sphere, will it change?
It's a sphere, but we're just looking along a number line, starting at the center of one sphere and going to the center of another sphere. So it wouldn't change. All this geometrical stuff is true for a sphere, not a circle. So, does that make some sense? Right at the edge, going from 0 to 0.8. Now, part B is asking about the electric field. So what do we know about points 1 and points 3? What is the electric field at that?
0.
Why is the electric field 0 at those points?
Because it's all the charges are outside and it comes to out.
Yes. It's inside of a conductor and all the charges are on the outside and cancel each other out. Now, point 2, we're just 0.5 meters away from that charge. So the electric field at point 2 would be 9 times 10 to the 9th times 5 times 10 to the -9th divided by 0.5 meters, and that quantity squared. So we get 180 newtons per coulomb, and it points towards the negative charge. Is everybody okay with that? Okay, that's number 1. Let's talk number 2, the capacitor. So there's a question on the quiz that some things go along with this for as well. So here are the plates of our capacitor. I'm just going to draw it smaller. Is that okay with everybody? Draw it. I'm going to attach it to a battery. So, for this, the battery is going to supply constant voltage between the two plates. So if it's a 12 volt battery, it's not a 12 volt battery. It's a 10 volt battery. So we're constantly going to have a voltage of 10 volts on this capacitor from one side to the other. So the equipotential lines inside of this thing, if we're going to have 0 volts down here and 10 volts up there, what do the equipotential lines look like? A. Equipotential lines. What do they look like in there? Like a staircase. So the 3D thing would be like a staircase going up. But they would be parallel to the plates in here with increasing values towards 10, and they'd be the same space away. Is that good? All right. B says, draw the electric field lines. What do the electric field lines look like? We'll go a different color on that. They're perpendicular to the equipotential lines. And which way do they point? Up or down? They point towards the 0 voltage. Yes. Yes. So equipotential lines are equally spaced. The electric field lines point downhill or point to lower voltage when they cross at 90 degrees. So good with that. C, calculate the amount of charge on one plate of the capacitor. So, we have two things for capacitance. One of them is Q over V. Do we know the capacitance? Oh no. We can't use that to get Q just yet. Capacitance will be in farads. So instead of doing that, we're going to do capacitance equals A epsilon naught over D. We're going to get the capacitance. Then once we have that, we can find the Q. So, what's the area of the plates? 9 times 10 to the negative fifth meters squared. Epsilon naught is that 8.85 times 10 to the negative 12th. A lot of units with that. What's the distance separating them? 18 millimeters, which is 0.018 meters. If there's a dielectric in there. And so we'll get down to that in part E. Okay. So, is it okay? Jump the gun? Would you rather take a test? Okay. Say what? Yes. Until we put something in there, it's going to be 1. So if it's an air gap capacitor, the dielectric's 1. If it's empty space, the dielectric's 1. Air's like a tiny bit bigger, but it's going to be fun. So we plug all those numbers in, and we get some terribly small number, right? What's that terribly small number? .425 times 10 to the negative 14th farads. Now, that gives us the capacitance. Are we done? No, we need to solve for the Q. So, Q is equal to capacitance times voltage. So that's 4.4 times 10 to the negative 14th farads times 10 volts. So Q comes out to be 4.4 times 10 to the negative 13th coulombs. Any questions about how to do that? All right. Part D. Part D says calculate the electric field. So to calculate the electric field, are you going to do this? You don't have an individual Q. This only works for point charges. It's right, it's correct, but these aren't point charges anymore. You're right, I don't need that. That only works for point charges. Thank you, sir. Do I have point charges here? No, so I don't want to use that. What I want to use is that the electric field is the change in voltage over the change in distance. Do I have a change in voltage? Over what distance does that voltage make that change? 18 millimeters, which is 0.018 meters. So my electric field comes out to be 10 divided by 0.018, or 556. You can say volts per meter. That's just fine. Newtons per coulomb. We'll just go with magic on that. Okay, E, what we're going to do is take our capacitor. Let me get rid of this. We're going to take our capacitor and we're going to insert a dielectric in there. And we're going to describe how the answer to C changes. So, this whole time we're staying connected to a battery. And we're going to insert some dielectric material in there. So, because I insert the dielectric, what happens to the capacitance? The capacitance increases, right? Capacitance is A times kappa times epsilon naught over D. If I put that in there, K increases, so the capacitance has to increase, right? No, that would just be a conductor, and we don't do kappas less than 1. We wouldn't be able to hold charge. We actually have charge flowing in between there at a high rate, and it wouldn't work. It wouldn't hold charge. It wouldn't capacitate anymore. So, because the capacitance goes up, and capacitance is Q over V, capacitance is going up. How is, part C is asking about charge, how is the charge going to change if the capacitor goes up in this situation? What's the voltage doing? Can the voltage change in this case? No. We're attached to a battery, right? So while we're attached to a battery, that voltage cannot change. Yes, if it's disconnected, it can. So while we're attached, the voltage cannot change, so the Q has to increase as well. So let's do part F. F says, instead of sliding that piece of rubber in there, I'm going to take and squeeze them closer together. What does that do to my capacitance when I squeeze them closer together? So D gets smaller. What's the capacitance do? So the capacitance increases. If the capacitance increases, what is Q going to do? And the voltage is constant. Ever good with that?
Is there any way to explain to make these smaller?
Yeah. What if I were to instead pull them apart?
So they would be bigger.
So V would get bigger. Then capacitance would go down, and Q would go down.
Yeah.
So that would be actually pumping more charge back into the battery. Both of these things, since Q is increasing, is removing more charge from the battery. The battery's there to constantly do whatever it needs to do to keep the voltage the same. Now, part G is we're going to disconnect the capacitor before pushing the plates closer together. So now we're disconnected, and we have plus Q on one side, negative Q on another side. But there's nothing going on over there, right? So when I push these two things together, the capacitance is still going up for the same reason. But what's Q going to do? Q is constant. Q is constant because the charges can't just disappear. They have to go somewhere. Before, when we were attached to the battery, they went onto the battery. But now, there's no battery for them to go to. So the charges stay there. So the charges don't change. So V, if the capacitance increases, has to decrease. Voltage decreases. Does that make some sense? Okay. Let's do number 3. We're only on number 3. Is this helpful or are you guys bored by this? It's going to take about 50 minutes.
Is anything that keeps constants the same change?
No changes physically to the capacitor would do that. If I were to do a different battery, the capacitor would stay the same. Now the voltage goes up, charge goes up too. But physical changes to the structure of the capacitor, area, or distance, or dielectric constant, that would change the overall capacitance. All right, so now we've got 0 here, negative 4 microcoulombs at negative 0.3 meters, positive 8 microcoulombs here at positive 0.3 meters. So, is the potential equal to 0 at the origin? Justify your answer. No. Why is it no? Okay, that's not great reasoning. So because they don't cancel, is what you said, and you're talking about the graphs, what we need is a succinct, full explanation of why they're not 0. So why don't they cancel at the middle? It's a good place to start. Yes. So because the charges have different magnitude, the potential from each charge, that's voltage, Bryson, the potential from each charge is not equal at the origin, so they cannot cancel. Are we good with that? So, B, we got 2 places we want to calculate the potential. The first one is at x equals negative 0.2 meters. How many charges are near that point? 2. Negative 0.2 somewhere right here, close-ish. That charge affects the potential, and this charge affects the potential. Still have 2 charges in the vicinity. Maybe that's a better way to put it than near. It's closest to 1 charge, sure. Okay, so that potential is going to be, okay, 9 times 10 to the 9th. Is everybody okay with the 9E9?
Yeah.
I just feel like I ain't got time for that today, you know what I'm saying? All right, so 9 times 10 to the times negative 4 times 10 to the negative 6th coulombs. And then how far away are we from that charge? 0.1 meters. Plus 9 times 10 to the 9th times 8 times 10 to the negative 6th divided by, how far away are we? 0.5 meters. Because the point we're talking about is at negative 0.2. Okay? So, with that, our voltage comes out to be negative 216,000 volts. The next point is at x equals positive 0.2 meters. Set up in the same way. Is it okay if I go a little faster through this one? So we have 9 times 10 to the 9th times negative 4 times 10 to the negative 6th. But this time, since we're talking about this point right here, 0.5 meters away, plus 9 times 10 to the 9th times 8 times 10 to the negative 6th divided by 0.1. Okay, so you put those numbers in, and the voltage there comes out to be positive 648,000 volts. Then part C is sketch voltage as a function of R. Right? Is it okay if I kind of come up here and do it? Sorry. Okay, so -4, +8. So -4, is it okay if I use the highlighter too? It's pretty. -4 comes down like that, yes? +8 is going to go up, but it's going to be a much bigger slope, right? So should they cross at 0 or somewhere else? Somewhere else. So when we look at it, that somewhere else is going to be closer to the -4. And my +8 is a big slope kind of around that.
Why is it exponential?
Because it's that over R thing. So it's not exponential, it's that 1 over x kind of graph. And so as we get closer and closer to a charge, for one of these things, that number is getting closer and closer and closer to 0. That's why we approach infinity when we get on top of that charge. Now, if we shrink 0.8, if we were to shrink 0.8, that line would come over. And when that got to be +0.4, it would be to where it was crossing right at 0. Does that make sense? Because 0.8 is bigger, it pushes it to the side a little bit. Does that help?
Just because the electric field is not zero electric field.
No, yeah. So the electric field points towards the -4 microcoulomb charge in this whole area over here. The only place the electric field is going to be 0 is over here where we kind of pop back up over. There's a, that's not the right line. This kind of does this. At that spot, the electric field's 0.
They're not like I hope they point to point.
No. It turns out that what happens is because that's smaller, the overall shape of the graph will eventually match this shape of the downward slope from the 0.8. And so it kind of pops back up and then matches it. So imagine if that 8 was there and we had a really nice slope, and then we drilled down to get the 4. It'd come back up to a certain place. And where that popover happened would be the inflection point. It would be on the other side of that 4. All right, 4. That is not the right thing. 4. We've got two identical spheres, each mass m, possessing a positive charge, and they're very far away. Then they're pushed together till they're r apart. One sphere is held in place, and the second sphere is released. When it's very far away, again, it has a speed v final. So when they're together, okay, so A, we want the energy changes for the experiment. So 1 is when they're far apart, 2 is when they're close together, 3 is when they have now moved apart again, right? So when they're very far apart, how much potential energy do we have and how much kinetic energy do we have? Yeah. We don't have anything, right? They're so far apart that I can't get any R so big that I don't get any of that. R is almost infinity. And they're not moving, so the kinetic energy is 0. Then we push them close together. What happens to the potential energy? It goes up. They're both positive charges, right? QQ, that's positive potential energy. What about my kinetic energy at this point? It's 0. I move them from rest to at rest, distance r apart. This point would be now KQQ over r, whereas we had infinity over here, that's why it was 0. Is everybody okay with that? Now, this is showing a change in the energy of my system. What's doing that? Yeah, someone does work. Whoever's doing the pushing is doing work and adding energy to the system, pushing them together. And then, when they're released, what happens to all that potential energy? All that potential energy becomes kinetic energy, right? So the electric field transforms the potential energy to kinetic energy. And that value of potential energy becomes kinetic energy. Is everybody all right with that? And the kinetic energy could also be written as 1/2 mv final squared. Yes? I don't really want to do part C, so we're not going to. When they both move. Still have the same energy, it's just shared between the two things now. They have equal velocity. That kinetic energy and that potential energy are the work needed to do that. Since we're only given the mass and the velocity, that's the amount of work that we need to put into the system. 1/2 mv squared. In part C, they're both going to share that velocity now. Don't worry about that. Okay, 5, we have a picture. So I'm not drawing that, right? Boom. Five, picture. A's indicate the electric field at each of the 4 points. Now, the electric field, does it point towards higher voltage or lower voltage? Lower voltage. So at point A, is it going to point up or down? Up. This is 10, this is -10, -5, and 0. It's pointing downhill. That's a downhill spot. Okay. B is at 0 volts. Is it going to point left? Is it going to point up to the left or down to the right?
Down like this.
Towards lower voltage. Is everybody okay with that? Bye, Bryson. Good luck on your test. C, up or down?
Down.
D, left or right? D has to be left or right because it has to be perpendicular. It's not going to point up to the positive 10. It's going to point away from that. So the electric field points towards more negative or lower values of voltage. B for this is rank the 4 points from least to greatest magnitude of the electric field. So least would be where they're most spread apart. Definitely B. And then probably D, and then C, and then A. That's where they're closest together. Yeah, good deal. All right, now C is asking between which 2 points could an electron travel without losing energy? Did we skip C? I'm sorry. Is there a point where the electric field is 0 on this diagram? where the electric field is 0. Right where? Well, think about, we have 0 here and 0 here.
Oh, okay, so there's
And this is, so this is a positive charge, and this is a positive charge, and this is a negative charge, and this is a negative charge.
yeah.
So that's kind of in the, can you see that? Yeah. This is a negative charge, and this is a positive charge. Is that better? Positive charge and a negative charge. Does that make some sense? So that the electric field kind of is confused at that spot. It'd be 0. Right in the middle.
And also because the voltage is zero.
No. The change in voltage from here to here is 0. Does that make sense? If I go from here to here, I'm going from 0 volts to 0 volts. No change in voltage. So what? That does not mean that. Yes, there's no equipotentials in the area, but that's only because we're doing 1 volt increments. So if we were to continue drawing equipotentials, they'd just be closer together there. Yes, but that's because there's no change in voltage between those 2 points. No matter where you go here, there's not going to be a change in voltage. You're going from 0 to 0, or you're going from 5 to 5. No change in voltage in the area. There cannot be a field if there's no change in voltage. Okay. Sorry, I misheard that. Then part D says, is there a place we can move without a loss in energy?
Yes.
Yeah, so a change in energy is Q delta V, right? That's going to be equal to our work. That's going to be equal to our change in potential. So, what will those 2 points be? B to C, because there's no change in voltage between those 2 points. Okay? And then E, calculate the amount of work needed to push a -1 coulomb charge from point D to point A. Work is Q delta V. Is it what? It's huge. Yeah, it's really, really big. So it's going to be -1 coulomb, and then we're going from point D to point A. Voltage A minus voltage D, because it's the change in something. Final minus initial. So -1 coulomb times voltage A, which is 10 minus voltage D, 5. So 1 coulomb, sorry, positive 15 joules. Because we're going from, I'm going to do a different color. We're going from D downhill to A. Right, so we're moving a negative charge downhill. I have to push a negative charge downhill. That's why I'm doing positive work. Yeah. No, the negative charge wants to go uphill. I'm forcing it to go down because it's a negative charge. It's doing the opposite of what the slope is telling it to do. Yes, because it wants to go uphill. And yeah. All right, was it F? G. Suppose an electron, all those numbers, were released from rest at point B and traveled without loss of energy to point D. What's the velocity? Again, change in energy is Q. No. Look at F. Letters are hard, y'all. F. I don't want to do that electron thing anyway. Now, what if it were a path that took it through point C? Would that change anything?
No.
So if I made a detour and did that, no change.
I thought it said to go to C, and I was like, well, yeah, it will change or
Total delta V is the same when we do that. Okay? Okay.
This will be all.
We'll see.